I wanted to show you how we get the expression for the uh, frequency of a pendulum following the same technique that we used for the frequency of a spring in simple harmonic motion. So this is the derivation of the frequency of a pendulum, of a simple pendulum. And what we did is we used this concept of conservation of energy in the motion of the simple harmonic oscillator. And so we'll do the same thing with the pendulum that we did with the spring. So let's sketch our pendulum here. Here's a mass at the end of a string, and we'll just draw a vertical line here in blue to represent the equilibrium position of that when it's at rest. And here is the angle theta when it's at its maximum extent, and the length of the string is L. And we know that the energy is the kinetic energy plus gravitational potential energy. And at maximum extent, we have that the energy is just UG max. In other words, there's no kinetic energy when it's at the maximum extent. And so let's sketch that. Let's assume that right now we're at our maximum extent. I'll put a little theta max there just to remind us that that's our maximum extent. And I'm just drawing a horizontal line because the potential energy is what is gotten by the fact that as that ball swings back down to the equilibrium position, it'll be somewhat below where it currently is at its maximum extent. And so the vertical displacement of that thing, how far it is above its equilibrium position in the y direction, which we'll call h, that's the source of the gravitational potential energy that it has there. And let's indicate this distance here from the pivot point or the ceiling to the height that the ball is when it's at its maximum extent. I'm just going to give that a name. I'll call it D. And of course, when it's at the bottom, it's still on the string, which has a length L. So we see that D plus H equals L, or H is L minus D. And the reason we're setting it up that way is that we're going to be able to use trig to figure out that length D. So in the, what do I want to say? So, right, so the gravitational potential energy, and why are we going after H, is that the gravitational potential energy is mgh. So we're trying to get the gravitational potential energy when it's at its maximum extent, then we're going to get the kinetic energy when it's at the equilibrium, and the gravitational potential energy is zero. We'll equate those two things, and that will give us an expression for the frequency of the pendulum in terms of the properties of the pendulum that we've outlined here. So we have a triangle here. Now remember, theta max is small so that sine of theta max is approximately equal to theta max, of course, in radians. And S is the arc length. That's the distance that it's traveling, which is also the amplitude of this motion. And so at the maximum extent, we're trying to calculate the gravitational potential energy. We need H. So I've got a couple of triangles in my drawing up here. Let me go back and change ink color here. So I've got a right angle here. And from that triangle that goes from the pivot point to the, let's label some stuff perhaps, pivot point P, and I'll call that point here E, and I'll call this point A for amplitude. So the triangle that is PEA, for that I can see that D is L cosine of theta max. Okay, that's just the definition of cosine. It's like the component of L in that direction. It's the side that's adjacent to theta max, so it's L cosine theta max. I also know that from the full triangle, if I approximate S as a straight line, I have that S is equal to L times theta max. That comes from S equals L sine theta max. And so cosine of theta max, I have to express it in terms of sine, so I can get it in terms of theta max. Well, cosine squared plus sine squared of any angle is equal to 1. So that means that cosine squared of theta max is 1 minus sine squared theta max. So that means that cosine of theta max is 1 minus sine squared theta max to the 1/2 power. That's the square root. And in the small angle approximation, I can replace that sine squared theta max with just theta max squared. So that gives me cosine of theta max is approximately equal to 1 minus theta max squared to the 1/2 power. But from this expression, I know that theta max is equal to S over L. So then I can write cosine of theta max is 1 minus S over L squared to the 1/2 power. Well, now we're going to do another approximation that's an expansion of this expression. And since theta max is small, S is very much less than L. And so that means that S over L is very much less than 1. And that allows us to make this substitution or approximation that 1 minus S over L squared to the 1/2 power is approximately equal to 1 minus 1/2 of S over L squared. There are additional terms in that, but those additional terms have an S over L to the 4th power, which is really, really small because S over L is already small. You square it and then you square it again, you get negligibly small numbers. So this expansion goes on for an infinite number of terms, but we just keep that first one. So now we have that cosine of theta max is 1 minus 1/2 of S over L squared. And why did we want theta cosine of theta max? Because D is L times cosine of theta max. And H, the height that we really want, is L minus D. So that gives me H is L minus L times 1 minus 1/2 of S over L squared. So I have L minus L, that cancels, then I have a minus L times a minus 1/2 of this thing, which if I multiply everything through gives me H is 1/2 of S squared over L. And UG, the gravitational potential energy, is then just mgh, which then becomes 1/2 m g s squared over L. And the kinetic energy at the equilibrium position, the total energy equals the kinetic energy, which is 1/2 mv max squared, which is 1/2 m times 2 pi f times a squared. But a, the amplitude for a pendulum, is just s, so that gives us k equals 1/2 m times 2 pi fs squared. So now we have two expressions for the total energy, one at the equilibrium position, one at the maximum amplitude position, and then we can just equate those two things. And we get 1/2 mg s squared over L. That's the energy at maximum amplitude, equals 1/2 m times 2 pi fs quantity squared. That's the energy at the equilibrium position. The 1/2 m's canceled. The s squareds cancel. So that cancels, that cancels. The s's cancel. And that gives me g over L equals 2 pi f squared, or f equals 1 over 2 pi times the square root of g over L. Let me rewrite that a little bit better. G over L. Or the period t equals 2 pi times the square root of L over g. So that's just a derivation to see where those equations came from. In the book, it just says, oh, you just replace k over m with this thing, but it doesn't offer you any explanation for why. You don't need to know this stuff, but I just wanted to demonstrate that it's not coming out of nowhere. It's using the same principles that we use for a spring, but because of the geometry of a pendulum, it's a little bit more complicated to derive it for the pendulum than it is for the spring. But it's the same exact idea. And again, we see that the period and the frequency don't depend on the mass, and they don't depend on the amplitude. For the spring, it depends on the mass and the spring constant. For the pendulum, it depends on the acceleration due to gravity and the length of the pendulum, but not on the amplitude or the mass of the pendulum. That means if I take a pendulum to the moon, it will have a different period. If I take a pendulum and lengthen it or shorten it, it will have a different period. But if I pull it back a little bit further, or if I put a heavier mass or a lighter mass on it, it's still going to be doing the same period. So an excellent timekeeper.